So welcome to this video on proximal policy optimization. So what's the main motivation behind proximal policy optimization? So in the last video we actually introduced TRPO, so Trust Region Policy Optimization, and the main idea behind it was that we want to make the biggest possible improvement steps, while we also do not want it to step too far away from our current policy to actually omit that our performance of our policy accidentally collapses. And turns out that PPO addresses some of the shortcomings that we actually lined out at the end of the last video when we talked about TRPO. So instead of TRPO, PPO just uses first order methods applied with a few tricks. So you have seen that TRPO uses actually second order information, requiring implicitly calculating second order information for your gradients, which makes it very hard, computationally expensive in practice. PPO also turns out to be significantly simpler to implement. So if you have seen the pseudocode of TRPO and if you maybe try to implement it, you will see that TRPO, the implementation of TRPO can become very complex and complicated in practice. And at least empirically, PPO shows at least similar performance to what TRPO is showing. To introduce PPO, so there's actually two variants of PPO, PPO penalty and PPO clip. In PPO penalty, you actually have a TRPO objective with a KL penalization instead of a constraint. And in PPO clip, you do not really use any constraints in practice. You instead add a clipping operator to the objective function to remove the incentive to move too far away from your current policy. And as a spoiler, PPO is much simpler to implement and to understand, and at least empirically much better. And in this video, we will actually focus on PPO clip because it is much more convenient and it gives a real alternative to TRPO and variants of this. Okay, where are we actually so far? So in the last video, we introduced TRPO, which actually maximizes a surrogate objective subject to a constraint on the size of the policy update. So what you see in here, we want to maximize the expected return, and what we actually wanted to do in TRPO is we want to increase, or what you see is we want to maximize this term, which basically means is that depending on the advantage, we want to increase the probability of taking certain actions in a state under a new policy divided by the probabilities of taking an action in certain states under an old policy. And this is actually what we wanted to increase. And this was subject to a KL constraint. So we actually wanted the probability distributions of our two policies to be lower or equal below some threshold, delta, which is the definition of our trust region between our two policies. So we actually wanted to be our policies, we wanted our policies to be close in policy space. With theta old being the policy parameters before we actually updated something. While we did not really explicitly formulate the TRPO objective like this, you can reformulate it. But actually what we wanted to do, we want to measure how pi theta performs in relation to pi theta old using data from the old policy pi theta old. And yeah, what you will see is if you compare the original objective of TRPO, you can exactly reformulate the objective to this one. And how did we actually maximize this, or how did we actually optimize this? We actually applied conjugate gradient after making a linear approximation to the objective and a quadratic approximation to the KL constraint. So this was the KL constraint, this was the objective, and we made a linear approximation to this one and a quadratic approximation to this one. So to actually reformulate, or actually to start over with PPO, let's just reformulate this objective just a little bit. Let's just define the so-called probability ratio RT of theta. And just define it like this. So RT of theta is the probability ratio between theta and theta old, meaning that the ratio of, or the probability of taking actions AT and ST divided by the probability of taking AT and ST under an old policy P old. So if RT is larger than 1, then the probability of taking actions AT under ST is larger, and so the actions that we actually took are now more probable than they have been under the old policy. So if we put in this term, so if we put in theta old in this term, the probability ratio becomes 0, and the probability ratio will become less than 0 actually if some of the actions are less probable than they have been under the old policy. In other words, what TRPO actually maximized was the following objective. So we actually maximizes the probability ratio under our policy times the advantage that we actually expected from these actions. And we can also call this objective function LCPI, which is actually conservative policy iteration in this case. And what we actually did is we penalized changes to the policy that moved RT of theta too far away from 1. So we actually wanted we wanted actually with our policy to stay around the region of the old policy, and we wanted to change the probability ratios of our two policies not too much. So we wanted to have that around 1. And we can actually, so if we like boil it down to the probability ratio, what we actually do is we can actually come up with the PPO objective that we want to maximize. So while TRPO makes a really mathematical formalization of the problem and formulates it like from an optimization point of view, we can actually come up with something much more easier. So what PPO is actually wanting to optimize is this one. So let's build it up together. So the first term here is actually the TRPO objective. It's actually the surrogate loss function of conservative policy iteration in here. The second term inside our min term is actually the clipped probability ratio. So what we want actually to have is, out of this clipping operator, we want to have a clipped ratio that says that we do not want to be RT outside the interval of 1 minus epsilon and 1 plus epsilon. So if this actually happens, we want to just clip it. So if it is below, we want to clip it to 1 minus epsilon times the advantage. And if it's larger than this, we want to clip it to 1 plus epsilon times the advantage. So if it's 1 plus epsilon times the advantage, this minimal operator will be the large one, so this min would kick in here. And if and if the clipping operator would boil it down to 1 minus epsilon of AT, this will also be the min term, and the min kicks in and will select this one. So we want to go to in one direction, we will apply this one. In the other direction, we apply this one. And if we take actually the minimum of the clipped and the unclipped objective, the final objective is something like a lower bound on the unclipped objective. This is actually what happens in the case, and you can also visualize this a little bit in here. So depending on, so if your advantage is actually something positive, then L-clip will take a value that is on this, which is actually this one. And what you see in here is So L-clip will be positively bounded by a value in here, meaning that there will be no incentive to actually move the policy parameters to this probability ratio in here, because there is already a maximum. And what you see in here, so if the advantage is actually negative, it will also be clipped at this point, because then the min will kick in, and 1 minus epsilon times the probability ratio will be the final objective that is being maximized. So this is actually the clipping operator that helps you to just define that the parameters of the old policy and not the parameters, but the probabilities under the old policy and the probabilities under the new policy will stay in a certain region around to the old policy. So if implement such a clipping operator within a vanilla policy gradient algorithm, you can come up with something like this. You can just, in this case, you have just what you have seen from other policy gradient algorithms as well. So you collect a set of trajectories, you compute rewards to go and estimate advantage estimates and fit your value function. You compute the advantage estimate using your current value function. The new value function will be fitted in here. And what you just then do is you update your policy by maximizing over the PPO clip objective, which is just an update on your policy parameters of this clipped objective. So this G function, you can look it up in the paper. It's just a nice reformulation of what I just introduced in the clipping operation before. So you just clip the advantage in order to make your policy updates more conservatively. Yeah, so it seems like much more simple than TRPO, although in general being similar in the main objective that it's actually followed by PPO. And what you actually see is that if you apply PPO clip to some well-known, in this case Mujoko, so this is robotics tasks, and if you apply PPO clip and you compare it to other well-known algorithms from that area, you will see that PPO clip performs really decent on a number of tasks. So this is well-known Mujoko tasks, and you see that PPO clip in these tasks outperforms usually any of the baselines that have been in place before PPO clip actually has been introduced. So you see TRPO is the sign form in here, and you see PPO clip being much performant in practice on most of the tasks, because it's actually using only first order information, and it's much simpler to implement. Also some nice videos in here where you can actually, if you go to OpenAI baselines, you can actually see some nicely trained humanoid robots that are actually really only optimized with PPO and the simple PPO clipping objective. PPO is a very simple algorithm, but now some practical consideration that makes PPO much more attractive after all in practice. So if you define PPO something like in a pseudocode, which is similar to what we did in the beginning, what you actually have is you run in iterations and you collect data, and you actually collect your advantage estimates, and then you optimize your surrogate target and fit your new value function and things like this. But it turns out that you actually have two alternating threads in PPO. The first thread actually lets the policy interact with the environment, so let the policy collect data, compute advantage estimates using a previously fitted baseline estimate. And the second thread actually collects all the experiences and then runs something like, for instance, stochastic gradient descent to optimize the policy using the clipped objective function. And it turns out that this allows a lot for parallelization and also distribution of your task. And this actually manifests in a system called OpenAI 5, which has successfully used to actually play Dota 2 on a human level experience. So in this case, you see something like a high-level architecture of OpenAI 5, which at the core uses actually PPO to optimize the policy. And what you see in here, you can actually run everything asynchronously in practice. So you have a bunch of rollout worker that usually use CPUs to actually process and to actually collect experiences using the current policy. And if you have all the experiences gathered from your policy, you can just collect all the rollout data and run on a single GPU machine your optimization using stochastic gradient descent. You can update your model parameters that's actually describing your policy, and then you can actually distribute your policy to the rollout workers to actually keep on doing the iterations. So this really nicely works in practice. And you can really distribute all the work to actually perform updates to your policy. However, you need to be sure that you do really frequent updates of your policy network so that the workers always work on the latest version of your policy. However, there is also one more thing actually that I did not mention about PPO because I wanted to simplify it a little bit. So the actual PPO objective looks a little bit different. What we just had, we had the clipped objective function, which we introduced in the beginning. However, the final objective of PPO has two additional terms. So this is the clipped surrogate objective. We also have a squared error loss for our fitted baseline function V, and we have an entropy bonus that actually favors a little bit the exploration. And the question is, why do we actually do this in a combined loss function? And the nice idea is actually that using all these, like optimizing all these things, actually requires similar features. So you actually require similar features to represent your policy network and also to represent your value function. So this is actually something that if you define it in a single network and you define it like as a distinct loss function, you can optimize a network with several heads, and the auto differentiation framework of PyTorch and related libraries will take care about where all your gradients actually optimizing things. And in case turns out that OpenAI 5 also shares the parameters between the value function and the policy function, which can then easily be implemented using a combined loss function that PPO introduces. Yeah, so if you're more interested in PPO, I really recommend checking out this page in here. There you see like videos and more information about how OpenAI 5 is actually working and how they actually made it train to play Dota 2. Some high-level information on that for the end. So what they actually did is in OpenAI 5, they actually had 180 years of self-play experience per day in Hero, meaning that we actually processed 900 years per day. There's no human data input. They have like, I think 256 P100 GPUs and over 125 CPU cores that they actually use for the rollout workers. This is some statistics that you can also find if you look into OpenAI 5. But you see, this is something like a large-scale experience that shows that PPO not only works for smaller Muchoku-based robotics tasks, but also for large-scale and high-dimensional image-based strategy games like Dota 2.